everyone for coming to our seminar today. So we are very happy to have Albert Fannjiang from UC Davis to talk about Tychography theory and algorithms. And I hope I pronounced appropriately the name here. So thank you, Albert, for joining us.
You did. I don't own that word, so it's okay. Okay, thank you for inviting me. So giving me an opportunity to talk about some of the things I did and other people did in the last few years. Most of the talk will be a chapter is actually taking out a chapter from the review article that I wrote with my colleague, Thomas Stromer. So most of the material, you can find it there in that one place. Okay, so I'm going to start with, because tychography is a form of coded aperture phase retrieval. So let me review what has been done in this more simpler area and very important area. So phase retrieval, you have a wavefront. I normally call it mask throughout my talk, because that's something you can maneuver optically or even with X-ray. To change the wavefront of the incident wave, and then once you hit the object, then the scatter wave is propagated forward, and then you take a picture of that scatter wave, and because the frequency of the light, so most of the camera, or I would say by now so far, if you in the X-ray regime, almost all camera can only take the intensity measurement rather than the full amplitude measurement. So the whole process is that you have impinging wavefront or mask, and then you hit it, the scatter wave is propagating, and then you have intensity measurement. A very simple setup, and the beauty of that is precisely in simplicity. And that's why a lot of people put a lot of hope in this kind of measurement scheme, because it's simple. Now, when I say simple, obviously there are a lot of technology involved, and actually very challenging also. Okay, so simple is a relative term, but at least in the setup, it's very simple and very easy to understand. Okay, so X, I call it mu-coded diffraction pattern. Mu is a wavefront or mask. When we look at the wavefront, the incoming wave right at the at the doorstep of the object wave. So looking at the product, the pointwise product, I'm going to work with a discrete object in my talk. So this will, if f is a vector, this will be a vector, this will be what's called Hadamard product. And then phi is a Fourier transform representing the propagation. Intensity simply means the amplitude square, modular square of the amplitude. So it's mu-coded diffraction pattern. Coding is very important in this problem. Okay, so what will you do if you have one randomly coded diffraction pattern? So this has been done a while ago. If you have one randomly coded diffraction pattern, I specify what random more precisely later. You don't have to have that. This is just for theory, for proof of uniqueness theory. All right. So then once you have that, then you can prove that you reduces to 3 different kinds of ambiguity. First of all, you could have a constant phase. Okay, you could have constant phase like that. And so basically you change your F to with a constant phase. Obviously, it's not going to change diffraction pattern. You can have translation. Translation also doesn't affect the diffraction pattern because it's created e to the linear phase factor, and linear phase factor have modulus 1. Likewise, a conjugate inversion, right? You could inversion referring to the minus sign here, conjugate referring to that, complex conjugate. That too also can be checked to correspond to the same diffraction pattern. What this really does is just taking the z, what's called z transform of f, which is a complex value function. You take the complex conjugate. That's all. Anyway, so with one randomly coded diffraction pattern, you can reduce ambiguity to the 3 very simple cases. And then one thing there is to say, hey, this shouldn't matter, because if I do any numerical work properly, constant phase is not going to change my visual, let's say, visual quality of the object. Neither does translation, because it's just shifting the whole thing. And the complex conjugate probably just change very minorly. You flip it, you kind of look at mirror image. So sometimes this is called twin image. All right, so these are the very common ambiguity that people working in the phase retrieval know a lot about. Now, however, okay, so let's look at the unique theory. So what can you do to eliminate all three of these so that you only have constant phase alone? Well, you need a little bit of redundancy. It's well known that if you only have one diffraction pattern, you always have these three, at least. Okay. Now, however, the theory says that if you have one plus a little bit, you will have enough redundancy to have uniqueness. Okay. Now, because in this talk, I primarily focus on a diffraction pattern as a whole, as a one measurement. So I'm counting the number of diffraction pattern. So I'm not going to go into the detail here. What does 1 plus mean? You can go look at the paper, my paper 2012 that specify the 1 plus mean, what does exactly mean. So here I would just say, okay, what if you have two independent coded diffraction pattern? Then the object is uniquely determined by those data up to a constant phase factor, which is probably 1. So again, here you need two independent coded diffraction pattern. Okay, all right. So if you were to count one diffraction pattern as a one measurement, so you need basically two measurements, two set of measurement. All right. So what about noise stability? Now this is the area that has been lacking any theoretical progress whatsoever. Okay. So here I'm dealing with Fourier transform case, the Fourier case. The only thing that I know of that can prove noise stability in the sense of if your data has certain noise, then you can control the underlying estimation by certain error bound. That kind of noise stability is only known in the case of a Gaussian measurement matrix, maybe some other like Bernoulli matrix as well, but they're all random, totally random matrices, and they are constructed probabilistically. They have nothing to do with optical propagation. And they are good for the theoretical understanding of the thing, of course, to certain degree. And a lot of theory has been developed for this type of Gaussian measurement matrix. Okay, so the best result so far is that, you know, the number of measurements. So here we're not talking about diffraction pattern anymore, because this is not coming from propagation. So this is just looking at m by n matrix. And so the best result is that m is order n. Now, normally this order of the constant in front of the order, it can be estimated is not very realistic, but nonetheless, as far as the n tend to infinity is concerned, m only need to be a fixed a proportion of n for a noise stability result. So people can consult those results for this paper for that result. Okay, so so this is about Gaussian measurement matrix, noise stability, and empirically what happened. Okay, empirically one actually observed global convergence of numerical schemes, wide variety of globally convergent scheme. For example, very simply, you could have gradient descent. You construct your reasonable objective function, either the Gaussian one or the what's called Vertinger flow. We have opportunity to get to more detail once I survey these and get into the Tychography area. So right now I'm just kind of pointing these results. Sorry for the people who are new in this area. They might find this rather abstract and remote. Okay, so gradient descent, like alternating projection, that's a very well-known gradient descent algorithm, or Vertinger flow. Now, for this to be globally convergence, at least in empirically, then you also need a special initialization method. So special initialization method, such as there are 3 classes of initialization method. One, the earliest one is called spectral method. That basically take the data, which is I'm gonna speak again in terms of the diffraction pattern, right? So diffraction pattern, use the diffraction pattern as a weight, and you construct and measure matrix together, construct a new matrix and look at the leading eigenvector, and using the power method to compute the leading eigenvector. That's roughly called the spectral method. As it was invented by these guys, and it became a impetus to a lot of other initialization method. Turns out initialization method can work extremely well. For example, null vector that my colleagues and I come up with, and then optimal spectral method that with these Stanford group and the group at Harvard and colleagues, they all have not just empirical performance, but they also have very interesting theoretical guaranteed. Now, again, for Gaussian random matrix, okay, no one has come up with anything theoretically about how this initialization method works for actual diffraction pattern. Okay, now optimal spectral method is very promising. It's particularly well performing when you have more than 2 diffraction pattern. Okay, once you stay at the 2 diffraction pattern, the null vector actually work much better. Here I'm plotting, the phantom as an object, do 2 diffraction pattern independently coded and measure, and you use that to do initialization. So even for very simple initialization method, such as null vector, you could almost reconstruct the object already. So this is a real part. Well, I mean, we because there's a constant phase factor. We adjust the constant phase factor so that it matches. But once you adjust the constant factor, you can see that they recover very, very well here. And this is just residual, basically a very noisy residual. But if you work with optimal spectral method, you can barely see the recovery. However, once you add another diffraction pattern, this guy works extremely well. Optimal spectral method, it beats all the previous 2. For all these 3, 4, even 5 diffraction pattern, the original spectral method no longer work. It requires a lot more data. Or you have to work with a Gaussian measurement matrix. Okay, so unfortunately, this is also not gonna go too well. Sorry, I'm falling asleep here. If you work with blind phasing, in other words, this is the main topic of my talk, is about blind tychography, meaning that the impinging wavefront is unknown. In that case, as far as I know, none of these initialization methods work very well. It really requires the knowledge of some underlying random wavefront in order to do the initialization well. Okay, so now as far as I know, if one were to get rid of this 2-stage algorithm, you want to come up with one method that actually converge globally and linearly, meaning pretty fast, linear convergent result. Then I would say the ADMM and Douglas Rockford splitting method work the best, at least empirically. Okay, so there are a couple of, I will mention just the one that invented by Luke in 2005. It works very, very well. And ever since then, it became a very popular algorithm in the physics community. Luke is a mathematician himself. in the University of Heidelberg. And then a couple of years ago, we come up with another ADMM method I have a little comparison of the performance. And these are the more traditional. So the blue curve is more traditional, called standard Douglas-Rutherford method. And the red curve is the Luke's what's called RAAR is called, yeah. So let me get to that later. But this is Luke's method. This is our method, the green curve. Now the blue curve is, I'm sorry, the red curve has an adjusted parameter. So this has been adjusted to optimal performance entirely based on empirical fact. Now the green curve is more or less optimized also by adjusting some parameter, but we have, for our algorithm, we come up with a way to determine the optimal parameter, at least in principle. So there are certain implicit scheme that can allow you to guess what the optimal parameter is. Okay, now how about convergence result? I'm sorry, I shouldn't perhaps use my iPad. Keep falling asleep. Convergence proof of any of these results is lacking in the case of diffraction pattern. So, for example, for Fourier case, 2 diffraction pattern, I only know of a local convergence result, and for global convergence result, one can come up with not these well-performing algorithm, but something that's suboptimal algorithm that you wouldn't use it for in practice. And you have to put a lot of condition on that kind of algorithm. So their global convergence result exists even for Fourier case with 2 diffraction pattern. As for example, I refer to this paper. But however, this kind of paper is tend to be more like an optimization methodology applied to the phase retrieval algorithm. So the result of that always fall into the following flavor that okay, once your objective function satisfies certain Lipschitz differentiability condition and other control coerciveness, and then you could have convergence of the iterative scheme, and the iterative scheme will converge to some stationary point. Okay, normally that's how it goes. Those theory usually does not say, well, that stationary point is a true object, because that's not usually what the optimization technology is trying to address, right? When they apply that methodology to inverse problem, they don't necessarily address the case where when it converges a stationary point, well, that's great, but is that stationary point the true object? Well, that's a question that people working the inverse problem is really concerned about, is that when your algorithm stops, do you actually get something that is very close to the true object? Now, this is the question that a typical optimization paper does not address. Now, however, global convergence, if you have a Gaussian case, I say the many diffraction pattern, that's obviously the wrong way of phrasing it. What I meant is that Gaussian case where M is much bigger than N. Then you do also have global convergence of many of the above algorithms that are can be made practical. Okay, so tychography. Okay, so what is tychography? What is tychography? As I said, tychography usually refer to a scanning microscopy. So instead of having a diffraction pattern all at once of the whole object, so this is the sample or object, you have a scanning probe that take picture of the small part of it, and then as you move, as you scan, you let the probe position and the next position overlap to a certain degree. Okay, the overlapping is what provides the redundancy, okay, that is necessary to reconstruct the object. Okay, so if you have scanning probe that is entirely non-overlapping, then you're not going to recover the the object because that's even worse than having just one diffraction pattern, the whole diffraction pattern. Here you break the object into small piece, and you have to create a redundancy by overlapping the prop location or the prop area. Okay, so in mathematical term, you can think of this as a phase retrieval with window-free intensity. So that's kind of appealing for people working in the harmonic analysis. Sounds like this is a window Fourier transform, and you have the Fourier intensity of it. And so the question is that, can you do phase retrieval with, let's say, a window Fourier transform, for example, right? So there are a couple of things that are involved in answering this question. I lump it together under the banner of measurement scheme. Okay, so first of all, you have a window function, well, the prop function, or the mask, like what I previously used. So window function, what kind of window function? Can you do it with just any window function? Secondly, scanning pattern, right? Now here, I'm doing this what's called the raster scan, meaning that you move in the same direction or the two direction, right? Horizontal, vertical, but with the same step size. Okay, that's a typical standard raster scan. Okay, that if you have not worked in this area, you'll probably say, well, just do this. Would not work. Okay, so that's a fair question. So what is the best scanning pattern, for example? Or does the raster scan pattern work in this phase retrieval problem with window Fourier transform? Secondly, how much overlap do you need to do reconstruction? So I will focus on these three area and address, develop a theory to address these three area, at least so that we can get a relatively realistic handle of what you can actually do to do reconstruction. All right, so now my personal motivation is actually coming from this paper published in Science in 2008, and this is the plot that they show. Okay, so here these physicists, they have a reputation, tend to be bold. They'll do something that they don't know what actually would occur, and this is what they did. Okay, so in this case, they realized that they cannot control their prop very well. Okay, so the dotted line is the fixed prop using their algorithm, which is not very, I would say, not very effective, but nonetheless, that's what they have back then, and then they use their estimated prop function or the window function to do reconstruction, and that's a dotted line. Okay, the dotted line or dashed line, I think this is for different algorithm, I think. Okay, anyway, they more or less, they don't perform very well. This is residual, relatively residual in percentage, right? So you're looking at least like 30% residual. So, and it's not coming down. So, I mean, from a mathematical point of view, we wouldn't call that a very good reconstruction, but they're quite happy, relatively happy about that. But then they found something even more shocking, is that once they have a very simple step to update their prop estimate from their initial estimate. Okay, so as you do the reconstruction, it's an iterative scheme. You also add a step that update your prop estimate based on your current reconstruction. Okay, somehow, even though these guys are product, right? I mean, they're multiplied together. So you will think if there's a uncertainty in one part, it will transfer the uncertainty to the other part, because after all, you're making a product, and your diffraction pattern can only recover the product, right? Somehow, right? So how does that work? I mean, normally people wouldn't think that this is possible to improve the result, but actually they did. So they did with the update of prop estimate, they encountered initial high jump, sharp jump increase of the relative residual, but after a while, it lead to a lower level of residual, 32% to 18%. So that give people hope that, or maybe that you can improve the algorithm and maybe you can reconstruct both of them all at once. But that, to for people working in the inverse problem, sounds to me is pretty exciting. So, okay, so maybe there's something going on there. All right, so basically simultaneous recovery of the mass and the object. That's referred to as a blind reconstruction. All right, so let me shift it because I don't know how to get. Hopefully keep it awake. All right, so I mentioned that the old ineffective algorithm, 2017, the people in that working in that area in University of Sussex, their group, they improved the algorithm called RPi. So that was an original result, relative error, doesn't converge very fast, and they are able to make it convergent faster. And however, this faint green light simply means that this is the solid green line is the average of that. So in other words, the actual performance is highly fluctuating. And this is just average of like, I don't know, a couple hundred runs. Okay, so in actual curve, it could be very crazy like that. Okay, so anyway, let's speak about the effectiveness of the algorithm, but nothing about the theory. Again, here for their run, they use the overlap threshold 70–80%. So that's going to give you a sense what you can hope to achieve, theoretical at least. Okay, so I'm going to set up some math symbols. Hopefully that will not be too confusing. First of all, I have to look at all the shifts I'm going to have, and I'm going to give myself a great degree of freedom to design the shift. It doesn't have to be raster scan. So I'm going to collect in the script T all the shift I'm going to use in my tychography, starting from the initial one. Right? So pick any initial one, and I can shift it. Okay. So raster scan, you can say, is generated by some cyclic group of two generators. Okay, I'm going to put a 0 here as the initial mass location. Mu t is the translation, so it's a shifted one. Okay, and I'm going to call M0 the side, the area of the probe. Of course, for math convenience, I'm going to use the square mask, even though in practice people normally use a circular mask or circular probe. Okay, so ZM square, M is represent the size of each side of the scanning probe. Okay, MT will be the shifted one of the mu t, and you can collect all these probe area and look at the union. That would be M. Again, F sub t is a object restricted to that part that is being scanned by mu t or mt. Okay, that's called ft. So it's the object part, right? This is a part of the object that has been scanned at the moment. Okay, I call that twin image. Is actually a 180-degree rotation of that, so that corresponds to the conjugate inversion. If you put all the object parts together, the union, then you have the original object. Okay, and you know, obviously you want the whole object being covered by all the scan. Then of course the subject, the support of this object should be inside this M. Okay, so in other words, you can think of tychography as a scanning microscopy or imaging that breaks down the original object into a set of overlapping object parts. Okay, so remember because MT, we hope MT and its nearby probe will be overlapping. So FT are not destroying, right? FT is not destroying. They will be also overlapping. Okay, so they are overlapping object parts, each of which produce a coded diffraction pattern coded by mu sub t. Okay, so that's my kind of brief way of thinking about my measurement scheme. Let me take away, I don't want to keep falling off. Let me use my desktop. Okay, that's better. Okay, so the first thing is that let's just look at how the raster scan can be described. Well, again, for raster scan, because the secret group of 2 generator, we can label this shift by 2 indices, right? K and L, because I'm talking about discrete object. So I think of a tau is a step size, could be 1 or 2 or some integer, and then K and L's are arbitrary integer as well. Okay, so I can represent my shift in this way. And so my M, I'm going to apply for theory development, I'm going to apply periodic boundary condition. Because think about the question that once your probe is moving to the edge of the object, what do you do with the part that is not overlapping with the designated object, right? So I'm going to apply the periodic boundary condition to do it other way. So in other words, I'm going to have a Zn, the discrete torus, in other words. Think of discrete torus as my object domain. Okay, so I apply periodic boundary condition for the convenience of the theory, of course. As before, my actual mask take up m by m square lattice. Okay, and that can be moved around. Okay, move around by this 2 indices shift raster scan. So that's a simple description of the raster scan. Right, now it actually more useful is to think about measurement scheme as a graph. So for example, I'm gonna look at, so raster scan, first of all, raster scan, if you look at the center of the probe, it take up a certain position. So raster scan will have this, we create this regular lattice. Okay. Now I'm gonna look at a case where I have a raster scan here. This is the first probe. This is my object domain, right? The second probe will be moved to here, right? And the third probe will be moved to here and by periodic boundary condition and there as well. Okay. So for example, you have a case like that, and likewise in that direction, that's the first probe. I shift to this and shift another time, then you cover this part together with that part by periodic boundary condition. So think about this as a torus, you shift this probe around, okay? Now, if I overlap enough, I need this, I said, so I use the node to represent the location, if you want, of the probe. So for this measurement scheme, this probe is represented by this node, and this probe is represented by this node. Okay. Likewise, so I did not draw the other one that shift and wrap around here. I only draw that what we can see here. And likewise, this is represented by this, and this probe is represented by this knot. Okay. If they satisfy this condition, MT and MT prime, the 2 adjacent, if the 2 adjacent probe overlap with the support that has the cardinality s greater than 2. All right. So if your probe overlap, but there's no object pixel that in the overlapping region, then your overlapping region will not do anything for you. Okay. You really need the presence of the object support in the overlapping part of the probe in order to create redundancy. So that's very important. But the condition we need is actually very minimum. Just okay, you at least need 2 pixels that are in the overlapping probe. So whenever that happens, you call that 2 knot S connected. Okay, so S could be greater than 2, could be 1,000,000, so on and so forth. So S kind of label that amount of redundancy in that node. Okay, so if they are all connected, then you can draw the edges between those connected nodes. And so you have a graph, and this is a kind of a complete graph. You can see that if object has this is the whole object support, every single pixel is non-zero, then you can see that this and that. And now, of course, when I draw this, there are a lot of pixels, assuming, right? And then this is the size of the prop. It doesn't mean that this is only a 2x2 matrix, right? This could be m by m matrix. Okay, it has a 50%, basically 50% overlap, right? So this prop and this prop have 50% overlap. This too has a 50% overlap, right? The nearby prop anyway. Now this is of course less than 50%. It's only a quarter, 25% overlap. So if the object is full, then obviously your S will be greater than 2, and then you can draw edge between any pair of nodes. So if I give you a measurement graph, you can kind of know how my measurement is carried out. So it's a convenient way of representing the measurement scheme. Okay, so here it is the theorem that we can prove. So if the tychographic graph is S connected, S greater than 2, in this sense. So in other words, if you draw, so for example, you can draw, this could be a graph, right, representing the measurement scheme, and clearly this is not connected, right, because there are 3 separate components. So here, if the tychographic graph is all connected with S strength, right, and S has to be greater than 2, right, and if the non-mask, here I'm not doing blind tychography, I assume the mask is known, then you can show that, again, there are some generic condition like F, the object part cannot be a linear object. It's annoying condition, but it has to be there, or one has to put other condition as well. So here I just assume that the object is not linear. Non-line means that it's not part of a line, in other words. It has to be basically kind of 2-dimensional, so to speak, at least structure-wise. Okay, and then the object can be uniquely determined up to a phase constant by the tychographic data. Okay. Now these 3 mathematicians come up with a uniqueness for standard raster scan with a standard Gabor window function. Now here, my theorem requires independent random measurement, random prop. Here for the standard Gabor window function, they also a uniqueness result, but they have to assume that shift is by 1 pixel at a time. So this is the maximum amount of shift. Okay, you cannot just work with like 50% overlap or anything. Here in my theory, it doesn't matter how much shift you have, as long as your overlap has a strength S greater than 2. Okay, so this is the difference between the 2 results. They each has its own strength and advantage and disadvantage. So again, I point to the fact that you can use graph to represent your measurement. And here I point out again, when do you have a 2 overlap window but no connection, right? Well, here's a 2 window. If you take 2 prop here, but the overlap is entirely black, right? Then even though the prop overlap, it will not provide a useful redundancy that is necessary to recover the underlying object. Okay, so you can see that this is a very sparse object because a lot of dark or black pixel, meaning 0, meaning that they are not part of the object. Okay, on the other hand, if you work with something that is more full in the whole domain, then no matter how you place it, you'll probably, and if your window overlaps sufficiently, you'll probably satisfy this connection requirement that I explained. All right, so graph representation. Now, I would say the raster scan, with what's called Fresnel mask. Fresnel mask is this quadratic face mask that is very commonly used in physics literature as well as experiment. Because this is what we create with a one point source, right? And use a Fresnel approximation. Well, that would be the wavefront. So it's very natural. If you don't do anything and you just use the point source to create the wavefront, okay? And then basically you have a Fresnel mask, okay? So this is very natural and almost the first thing one would do, in addition to the plane wave, of course, right? Plane wave would be constant 1, for example. Here you create a certain curvature in the wavefront, but again, can be very easy to create it. So here I'm drawing the two different Fresnel masks. This is with M or rho very small, and I think it's maybe I have a number. I don't have the number here. Rho is small here. Rho is a little larger here. You see the typical ring exhibit here. Of course, I'm looking at the real part only. Otherwise, you wouldn't be able to see that it has a modulus 1, for example. Now, so here I want to point out that with the raster scan, now here I point out the Gabor window function is very close to the Fresnel mask case, okay? Except this is a Gaussian window function, and this is the imaginary Gaussian, okay? Now this require 1 pixel movement at a time, very refined movement. Here, if you don't do that refined movement, okay, here I'm doing 50% actually overlap. You can prove, we come up with a counterexample. We construct a counterexample that show that the uniqueness cannot be achieved. And moreover, that actually manifested in numerical simulation. Here, this is a relative error and relative residual. Blue is relative error, red is relative residual. You can see as you change, this is the row, I think. Yeah, so with the row from 0, 1, 2, 3, 4, you can see every time row hit an integer, it has a kind of resonant phenomena that happen. The error just jump up to almost 1 here. If you stay outside of that integer or their neighborhood, then you will get much better reconstruction. This is a different number of prop. Similar phenomena happen. So you can show that for that kind of mask, no uniqueness, right? When row belongs to a discrete set of values, right? Except in the case of 1 pixel shifts, like in the case that I previously mentioned, right? So that tell you what? The mask is very important. You have to pay attention to your mask. You cannot just pick arbitrary mask or the standard mask, because and the hope that with a very small overlap or very large shift, you can still reconstruct your object, even when the mask is totally known. So this is the case where mask is totally known. It's not even blind tychography. You already lose uniqueness for certain value, discrete value of row. Okay, so now let's look at again, go back to the blind tychography. Okay, so blind tychography had this fundamental ambiguity that you can never hope to get rid of. Okay, it's called affine phase ambiguity. To think of the original mass is mu, original object is f. Now suppose you change your mu by this affine phase. Okay, w is a fixed vector, integer value vector. N is, of course, the pixel. Again, I'm looking at 2 dimensions, so n again is belong to Z2. And you can modify your mu mass by this linear factor or affine phase factor. you can modify your object by a different affine phase factor. The linear part is the same, except with a sign change. The constant part can be arbitrary, okay? And then you look at the product of that after shift. You shift new, and you look at the part that is covered by shift new, right? It's called GT, right? So the new T, GT make the Hadamard product. You can do a quick calculation, algebraic, simple algebra. You can see that this linear part cancels it entirely. Well, not quite, only the independence part. So the point is that now the product of that is the product of original mass and original object times a constant phase and another constant phase. Now, why do I say it's a constant phase? It's a constant phase because it's independent of n. So for that particular diffraction pattern, this acts as a constant phase, meaning that this guy will have the same diffraction pattern as that guy. However, this phase is different from that phase because this phase, even though it's constant for t fixed, well, it depends on t. So as t changes, this phase also changes, right? Kind of arithmetic progression with respect to t, okay? And so this is what people refer to as affine phase ambiguity. And this is inevitable. Like in the case of phase retrieval, the best you can do is construct object up to a constant phase factor. Here, for blind tychography, you can only hope to construct object and mask with a affine phase factor, right? Like phase factor like that. That's the best you can do. And this calculation illustrates that. Okay, so for developing theory, you can only hope for necessary condition. We kind of look at it because we know that this will happen. So the first step, we shoot for finding a condition to ensure the following condition holds, necessary condition holds, meaning that the mass estimate and the object estimate, when they make the Hadamard product, right, there will be some phase factor that depends only on t and not on underlying pixel, right? So we say, okay, let's shoot for that, try to find a condition to ensure this happen, okay? I refer to theta t as a phase drift, okay? Because it does drift typically when t changes, theta t also changes. So it's not a constant phase factor, all right? So this is what we can prove that, here I'm going to point out that in the case of cyclical group of order, Q, so like raster scan in other words. So here I prove the raster scan, the theta t must be form a arithmetic progression. So the theta t can be indexed by two indices, K and L, as I previously. Here I look at one cyclical group. So for example, one-dimensional raster scan, for example, here. Okay, so 1 and 2, then you have two indices. So here I only put one index. And then you can show that regardless whether it's one generator or two generator, you have a theta, the phase drift, that form an arithmetic progression. All right, so here's the main theorem for the theory is that to get the intermediate result, I call that intermediate result because this is not recovering object and mass separately yet, right? Not yet. They're still they still must be multiplied together. Okay, we're looking at this as a whole, the product as a whole, right? So I say, when can you have that? Well, you need a couple of conditions. First of all, you have to have your prop that has a tie support in actually one of the prop that has tie support. Secondly, you have to have your initial guess of the mass that lie within the acute angle of the original mass. So in other words, if you look at the inner product of the mass estimate and the original mass, the real part of that has to be greater than 0. So meaning that if this is the object phase, mass phase, original mass phase, and this is your mass estimate phase. The amplitude doesn't matter. The phase is important. The phase of the mask, the phase of the wavefront is important. That's your estimated wavefront. This is the original wavefront. You have to initialize your original the wavefront, right? So that the angle is less than pi over 2 in either direction. Okay, so that will turn out that this is almost inevitable. We will see the more example down there and in the following. But so here I refer this as a mask phase constraint. You need to have phase constraint. Okay. And other than that, then you can have that relationship with high probability, with exponentially close to 1. And the constant C depends on the mass phase distribution. So it also depends on your random mass phase, how they distribute, and the distribution of that. For example, if you have a very rigid delta function, of course, your C will be very bad, actually. May even be 1. I have not looked at that myself. But as your phase random, the distribution spread more around pi over 0 to 2 pi, then your C will become more and more favorable. All right, so object support constraint simply, as I point out, simply means that you have to have one window that whose foresight touches the support of the object. Okay, so I consider that as a very minor condition, unless you're dealing with extremely sparse object. Even this, you can say that this satisfies the Ty support constraint because at every single side of the window, it touches the object pixel somewhere. All right, there's a counterexample that if this is not satisfied, you can show that the product of the object estimate and mass estimate will not be a constant or will not be a phase factor times the original object and original mask. Okay, and then for raster scan, so here comes the problem. For raster scan, one can show, so let me back out a little bit. So once I have an intermediate result like that, the next step is that I like to separate mu from F or nu from G, right? I want to see how I can separate these two. Right now, I only have the product, okay? So to separate the two, one immediately hit this problem with the raster scan. So this is bring up the raster scan problem in a very pronounced way. So think about the case where you split the F into 9 parts, for example. You can attach a certain phase factor to each different part in a different way. You can see this is a kind of arithmetic progression. And then you can counter, right? So this is your object estimate, right? And then you have the mass estimate that you have a counter phase factor minus here. And so when you make the product of G with nu, right? So this 2x2 part will cover this 2x2 part, and their phase factor will cancel each other. And then you will have this result, right? Nu times G equals some phase drift times mu times F, right? Satisfy what I call the phase drift equation, but nonetheless, you see that G is not a good construction of F. Nu is not a good construction of mu, and this is the construction is not even unique. There are many variants of this type. There's also even more serious, what's called periodic ambiguity. Physicists discovered that about 10 years ago, it's called raster grid pathology, right? So in fact, once you, let's say, split your mass in 2 parts, right? You can actually attach any phase of this form to the parts arbitrary and even pixel dependent, and then create a new object like that, right? And totally unrelated, well, not totally unrelated, but can be arbitrarily far away from F, right? You can manipulate this epsilon and make G very far away from F, right? And this has a periodic structure to it, okay? And that's why this is called periodic ambiguity. I call it periodic ambiguity. physicists call it raster group pathology. So in any case, to break that, you actually need random perturbation. So we come up with a mixing scheme. Let's say if you take a raster scan, you do certain, it doesn't have to be random, some irregular perturbation to it, okay? You can perturb it with what I call rank 1 perturbation. You only have one index. Here you can perturb it with the 2 indices, okay? The more, so this is a rank 1 perturbation, okay? This is a full rank perturbation. So you basically perturb your raster scan, and then we prove a theorem that shows that almost you just have to be almost slightly greater than 50% overlap. Then you can have this object estimate, and can recover the original object up to a fine phase factor. Well, also there's an amplitude constant also, okay? Because you start with the product, right? So you can not just phase factor, you can attach a magnitude factor as well on one side, and then divide the magnitude, the other side by a same magnitude factor. So that's a magnitude factor right there. So in any case, so you need a mixing scheme, what we call mixing scheme. There's a general definition of what mixing scheme are, and this is 2 examples of the mixing scheme that we actually can prove very concretely. We come up with a very concrete condition with about 50% overlap. So more generally, if the measurement scheme satisfies mixing property, then you have the reconstruction from blind tychography up to a fine phase factor, All right. So again, counterexample exists for perturbed raster scan with less than 50% overlap. One can rigorously construct such a math example. So you do 50% seems to be really the borderline case. Again, no noise stability, as I said. The only noise stability that I know is by these mathematicians that require the maximum amount of shift. Again, 1 pixel at a time, then one can prove noise stability for tychography with a gobble like window Fourier transform. So how do you use the theory? To use the theory is that the prop initialization. Okay, we use this as a prop initialization because, but this is speak about practical matter. This is to this day we're still working on this. Is how do you effectively come up with this initialization, the prop initialization, because this is what theory demands, that if this is the mass angle, this is the estimate initial mass angle, your estimation, then the angle has to be less than pi/2 in either direction. How do you, if you don't know, how do you, in other words, how do you come up with this mass initialization? It is a question that we're still working on. And I think my time is up, and I will skip all these algorithms that we developed. And let's go to the final conclusion. All right, so the first message is that blind tychography cannot be realized with a regular raster scan. It needs certain type of irregular scan that break the group structure, basically, okay, that we call mixing scheme, and that will demand the connected graph, the measurement graph, have overlap, roughly speaking, slightly greater than 50%. Now, even though the theory says slightly bigger than 50%, our numerics totally confirm that. One, we come up with an algorithm that work just slightly over 50%. Sometimes we even put slightly less, it will still work. Now, of course, that we are really at the edge of the the effectiveness, of course. So 50% is a very realistic overlap. Also, this is totally consistent with what physicists have come up with, the amount of overlap you require for doing this type of reconstruction. You need mass prior. This is probably the weakest point of the theory, is that you need this mass prior. And how do you, in a given situation, how do you come up with this mass prior, the constraint to find within the constraint your initial mass estimate? It is a very practical issue. Now, how do you extend? We have a way to think about, we're working on how to extend this to 3D tomographic phase retrieval with uncertain orientation. So it's like if you measure this, the 3D object, different projection, you also have certain overlap, right? So how does one use the overlap, the redundancy that the overlap provide in order to control the uncertain orientation? Suppose you don't know the orientation precisely. Just like in the case of blind Tychography, I don't know the mass precisely. How do I overcome that with a redundancy of data? So I think that this is a potentially promising direction. Since I have not talked about the algorithm at all, so I wouldn't go into the discussion of algorithm. I would just say that the blind Tychography algorithm, again, the main issue right now is how to do proper initialization method. Okay, so thank you very much for your attention. Here are all the references that I mentioned in my slides. So in case you're interested in looking them up, you can from this list. Thank you so much.
Thanks a lot, Albert, for telling us about this fascinating technology. So the floor is open for questions now. So please unmute yourself and ask questions if you have some questions about the talk here. So, but I was wondering, so for the mask, when in the blind case, so is there sort of drift of the mask, or could you consider the mask to be fairly stable over sort of a raster scan? So you have one mask to identify.
Okay, let's see. Let me try to understand your question. Are you referring to this?
Right. Yeah. So, so when, so for instance, is there some particular way or type of object that is used good for the mask identification?
For mask identification?
Yeah, I mean, or the probe.
Yeah. Let's see if I. With the probe. I guess I'm not understanding your question. Are you referring to an algorithm for reconstructing mask?
Yeah, for the blind case.
Are you talking about algorithm, right?
Yeah.
Are you asking about algorithm?
Yeah.
Oh yeah, yeah. Sure. There are very actually very well performed algorithm out there. Well, of course, no, we don't have a performance guarantee. For example, you know what I call we have a what I call the Fourier domain ADMM using you know, you set up your augmented Lagrangian, you go to the standard exercise. You actually every single step of the way can be solved very simply and effectively, and you could have you know extremely well performance. So just roughly speaking, so let's see what. So you have this B is your data. You introduce you know, two additional variable in the Fourier domain Z and Y. You're looking for Z whose modulus is given by B, and now you relax the constraint about the data by introducing the augmented Lagrangian. And then you go through the standard. So this is not the standard ADMM, I should say though. Standard ADMM usually don't solve two variables at the same time, right? The standard ADMM solve one at a time. But since we're addressing blind tychography, we have two variables. We have to solve it all at once. Now you might say, how is that possible? Does that even come up with a simple answer? Well, actually there are simple answer for doing this. You actually you can construct explicitly like that. So for example, the Z mu step can be explicitly given by this. Each case involves some matrix or its projection that builds on the previous estimate, right? Like next step is Y and X. X is object. Y is another Fourier measurement, data estimation. Again, a pair need to be reconstructed from this minimization. Well, it turns out there are explicit form for this minimization, right? So every single step of the way is totally explicit. In the case of, let me show you, for example, this is using about 50%. So that's E Gaussian DRS. So that's maybe a name that we give to the algorithm is that the 50% overlap. This is 66% overlap. This is a 75% overlap. Obviously, the more overlap, the faster the convergence. This is iteration, right? So if you look at the 50% overlap, you see that 200-300% step, you're there. So you look at the object error, you look at the residual, you look at the mass error, they eventually settle down to, this is a relative scale, relative percentage. So it settled down to pretty low level by doing this very explicit calculation. And as usual, if you increase the amount of overlap, okay, you make the convergence much faster. So this is about 100 steps, and it starts decreasing at a much earlier stage because you have much more overlap. So if you keep overlapping more, 75%, now you could get to almost, to much lower levels of error, which is a lot fewer steps. So there are another algorithm that we develop also that's slightly less well performing, but very similar. There's typically have a stage where you don't see a lot of improvement, and then if you wait for a while, then it all of a sudden it enters into this linear convergence regime. If you think about it, it's not too surprising because this is a non-convex optimization problem, right? So presumably you're wandering around in this wilderness, so to speak, not getting anywhere. Somehow the algorithm will enter that linear convergence regime. And then once it get there, it doesn't get out. It just go zoom into the object and the mass at the same time. So to answer your question, there are, as I said, I didn't have the time to talk about it. There are very well developed algorithms, but no analysis whatsoever for the blind case, because that's not a typical algorithm people analyze. But we just start having this, energy again to look at the algorithm, because maybe there are some interesting thing to be said in the algorithm. Already there are quite an interesting thing to be said, even in the case of non-blind tychography. The algorithm, the similar algorithm, when you supply the mass information completely, one can analyze a lot about these algorithms because it's so explicit. You look at these algorithms, they are very explicit. Like in the case of E Gaussian DRS, you can even write down the map. You can write down the map. Of course, it's a nonlinear map because the PB is a projection upon the data, and the data is the nonlinear data. Of course, that's a nonlinear projection. But this operation is actually extremely cheap. It's a pixel-wise operation. It just means that you take this Fourier object, you trim its magnitude to fit the data, because data give you the intensity, the magnitude. And that's all. So it's a pixel-wise, very fast algorithm, very fast, very explicit. And so you can analyze the fixed point, you can analyze its stability, but only when you don't have to update mask. Once you have to update mask, the analysis just so far, last time we looked at it, is way too complicated. We don't know. We didn't know how to do it. But if you have mask is supplied to you, then you can do a tremendous amount of analysis.
Great.
But again, no global convergence though. I mean, all these algorithms, once you work with Fourier case, you work with like a minimum amount of data. There just isn't global convergence in the sense that I want, not just like in the traditional sense that okay, all sequences converge somewhere, and that somewhere is a stationary point. That's a typical result in the optimization framework. And for us working in an inverse problem, we're not satisfied with that kind of result. We like to say, okay, if it converges to the true solution. Or if it doesn't, it's not the true solution, it's at least in the neighborhood of that true solution. That's what we want, right? In the context of inverse problem, no general optimization methodology or paper that supply that kind of result, as far as I know. Right, so that kind of result require local analysis. For example, you have to estimate. You have to show that the neighborhood near your point, your true object and true mass is attracting, right? That's a minimum you have to show. Attracting, right? Or the functional is locally convex there, right? And then it's non-local, right? And then the best you can hope is that, okay, how big is the basin of attraction is, right? So if you can establish certain finite size of basin of attraction, that seems to me the best you can do. And what if you get out of the basin of attraction? How do you guarantee it come to the basin of attraction? Well, that's to me is I think it's a very hard problem. Yeah. Now, so the general scheme will be like, you have a global but it comes to a stationary point, but this stationary point could be totally out of the basin of attraction of the true object, right? And so in that case, even when you have convergence, you still say nothing about reconstruction.
These sound like insoluble problems to me.
In a way, yeah, it is. We're trying to,
Basis of attraction. Well, yeah.
Yeah. Well, I would say though, now people did do that. In the case of Jim, you might know this very well-known algorithm invented by von Neumann back in the 30s about it. So you have to think about your feasibility problem. You have two constraints. You just iteratively and alternately project onto one constraint at a time and the other constraint, right? You do the alternating projection. Now that one, people have analyzed, a mathematician, Stephen Mallar's student, and himself, I think also, they work on the Gaussian case again. Gaussian case, they were able to say for that algorithm, establish a finite domain of finite size basin of attraction for the Gaussian measurement data for the problem of phase retrieval. Now, probabilistic estimation and so on and so forth. So people did try that area, but I haven't seen that being very successful in the context other than a Gaussian measurement matrix using probabilistic method.
Great. Any other questions for Albert before? Well, thanks a lot, Albert. It's a lot of very interesting
Yeah.
information here. Very
Nice to see you too.
interesting
Nice to see you guys too.
challenge.
Yeah.
Yeah. So
Stay healthy.
yeah, I will.
Here.